Alrighty, hello. So we are starting unit number 5. Very exciting. We only have 5 weeks left until final exams, so now is getting to the point where you're starting to see a lot of the chemistry pick up and start to really make connections between different things, and it also means that you're starting to reach the panic mode if you are still failing the class, and so that means you're watching these videos more because you are desperately trying to bring your grade up in class and make sure you do better. So this unit is going to be all about bonding, okay, and the way atoms bond together in order to become more stable. And so these types of bonds, there's going to be a few things. Bonding is another word for a force that combines two things, and there's going to be two types: intermolecular forces and intramolecular forces. Now, those words sound very similar, but the key thing that you're going to want to know is that inter means within the molecule, and intra means between molecules. Okay, so these first two things that we're going to talk about, ionic and covalent, are going to be the two types of intermolecular forces that we're going to talk about. So the first one is just, again, bonds overall. A bond is a force that holds atoms together. Okay, and so these atoms bond because they want to achieve a stable configuration with 8 valence electrons. Now remember, valence electrons is that word that I told you was going to pop up over and over and over again. And valence electrons are the electrons in the outer shell of an atom. So if you have your nucleus and you have your energy levels surrounding it, let's say we have 2 electrons in our first energy level, and we have 1, 2, 3, 4, 5 in the outer one. With 7 electrons, that would make this nitrogen. Okay, and we would count how many valence electrons it has. 1, 2, 3, 4, 5. It has 5 valence electrons. We also know that if we look on the periodic table, nitrogen is going to be in column 15. Column 15 means 5 valence electrons. Now, the ones that have 8 valence electrons are the ones in this outer energy level with 8, column 18, which is also our noble gases. They are the most stable on the periodic table. Now, these noble gases have 8 valence electrons, and this follows the octet rule. We talked about the octet rule briefly in the atomic theory unit, which was unit 3, but this is going to be popping up and going to be even more important during this unit. So there are two main types of bonds or forces that we're going to be talking about today. So ionic bonds form when one atom transfers their valence electrons to another atom, and it's usually going to be between a metal and a non-metal. Okay, so between a metal and non-metal. And remember, these valence electrons, if you were to draw the Lewis dot structure of atoms, so if we say sodium and chlorine, we know that sodium is in column 1, so it has 1 valence electron. We're going to represent that as a dot. Whereas chlorine is in column 17, so it has 7 valence electrons. So we draw 7 dots around chlorine. And sodium and chlorine have such different electronegativity values, or the ability to attract those electrons, that sodium is going to donate its valence electron to chlorine. It has a low electronegativity and a very low ionization energy. It wants to get rid of that valence electron, and chlorine wants to have that full 8. And so this would make sodium with a positive charge, because now instead of having 11 protons and 11 electrons, it's only going to have 10, so it's got one more positive charge. And then chlorine is going to be negatively charged. And this attraction between the positive sodium and the negative chlorine is going to create a force that will bond them together. Okay, and so if we look back at our notes, we see that it resulted in a positively charged ion, which is called a cation, because remember, cats have pos, and cations are positive. And it also resulted in one negatively charged ion, which is called an anion. And because those opposite charges attract each other, they come together and form that bond. That force between them causes them to create a bond. Now, some properties about these ionic compounds is they are also known as salts. Now, you may be thinking, salt. I just know about NaCl, which is on my french fries. But there's also magnesium chloride, which is also called Epsom salt. That's what you put in your baths when you're really sore and it helps relax your muscles. Even something like Fe2O3, iron oxide. It's a salt. It's an ionic compound. Now, it's not the most common ones, but they are all salts if they are ionic compounds. Now, a single entity of an ionic compound, or a single piece, might be a more basic word for that, is called a formula unit. And that word will pop up multiple times. So with a formula unit, okay, if I have a bowl, okay, so this is my bowl, and inside my bowl, I have several NaCl molecules, or excuse me, formula units. I have several compounds of NaCl. I would say that this has 4 formula units in it because I have 1, 2, 3, 4 in the bowl. Now, ionic compounds exist as a solid at room temperature, and they are going to easily dissolve in water. Okay, easily dissolve in water. Now, they are also going to exhibit a crystal structure. What this means is that the way they bond is going to form a pattern. So, for example, they might form bonds that kind of look square-like, where the bonds are the lines connecting the dots. Okay, that might be a type of structure that they would form. They're also going to have high melting and boiling points. And this high melting and boiling point is an indicator that an ionic bond is a strong bond. If you need a high melting point, that means you need more energy to break the bond. Okay, and so it's going to show just that high energy, those strong bonds and strong forces are within them. And they also can conduct electricity in solutions and have high electronegativity values and differences, which we will talk about later. And it's going to be greater than or equal to 1.7, which again we'll get to. But remember, electronegativity is the ability to attract electrons. So, some common ionic compounds are NaCl, magnesium chloride. KBr is used for dogs to help prevent epilepsy or seizures. There's all kinds of ionic compounds. So the next type of force or bond is going to be a covalent bond. And the difference with covalent bonds is that instead of transferring their electrons, 2 atoms are going to share 1 or more electrons between them. And it's usually between 2 non-metal elements. Okay, and so since electrons are shared, There's no charges, no ions. If it's an ion, it's going to be part of an ionic compound. Now, if we look at a covalent compound, for example, carbon dioxide, okay, or water. These are going to be our covalent compounds, but I'm actually going to look at something like a chlorine. Okay, now chlorine is a diatomic molecule, and it's going to share its valence electrons because we see that chlorine each has 7 valence electrons. It's in column 17. But they have the same electronegativity value. They're not going to be able to pry one electron off from the other. So what they're going to do is they're going to come together and they're going to share these 2 valence electrons in the center. And when they do that, we call it a single bond because there's a single pair of electrons, and we rewrite the pair as a solid dash to indicate that. Now, oxygen, O2, oxygen has 6 valence electrons. Okay, so this means when it comes together, it's going to need to share both lone pairs of electrons in order to complete its octet. And when it does that, it will have a double bond. Okay, now a double bond is going to be stronger than a single bond. Okay, and it's also going to bring those oxygen atoms closer together. And it can even go all the way up to a triple bond, such as with nitrogen. Nitrogen has 5 valence electrons. And so in order to reach its octet, it's going to have to share the 3 in between it. And so it would form a triple bond, which is the strongest of the covalent bonds. Now, with covalent bonds, and they're sharing, okay, they're not always shared equally, but before we get to that, let's talk about some properties. So they're also known as molecules. So I know a lot of times we use molecules to describe anything that is not a singular element, but molecules actually refer to covalent compounds, whereas formula units refer to ionic compounds. And they're going to have low melting and boiling points, which means that their bonds are not as strong as ionic compounds. And so with that, they're also going to be flammable. It's not going to take much energy to make them combust. They do not conduct electricity in water, and the reason why is because you have to have ions in there. And actually, if we go back up to our notes at the top, if my screen will scroll, here we go. One thing is that if it can conduct electricity in solution, anything that can do that is also called an electrolyte. So if you remember from like Gatorade and things like that, the reasons why you need to have electrolytes in your body is so that your brain can send electrical current to the cells in your muscles and things like that to tell it what to do. So when Gatorade markets as having a lot of electrolytes in it, it's because if athletes want to move faster or do things, they're going to need to have enough electrolytes in their body so their brain can send messages to the rest of the body. And so if they're not conducting electricity, they're also not going to dissolve as easily in water, and they're going to have low electronegativity differences. Now, diatomic elements, one way whenever you're looking at vocabulary words is to break it down. So di is the prefix for 2, and atomic is referring to atoms. So it's referring to how some non-metal elements on the periodic table exist in nature only as pairs or in groups of 2, which are going to be bonded covalently. Now, one way to remember this is I kind of pronounce these 7 as Hofbrinkel, Another way is if you look on the periodic table and you say, hey, there are 7 diatomic molecules. You look at number 7, which is nitrogen, which is one of them. And if you draw a 7 on the periodic table, you'll see nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and then hydrogen is over here. And so you can draw a 7 on the periodic table and look at 6 of the diatomics, as long as you don't forget about hydrogen that's located over here. So those are just 2 tricks. So either pronouncing it Hofbrinkel, which is, yes, of course, not a word, and it's a little silly, but it is there. And that will be how to remember it. Now, ionic and covalent compounds are going to be rarely purely ionic or covalent. It's always a spectrum, and it's determined by calculating the difference in the bonding atoms' electronegativity values. Okay, and so these forces that we've been talking about, remember, are intramolecular forces, or within the compound. Did I say that backwards at the beginning of the video? Let's double check Miss Nichols' craziness. I did say that backwards. So let's go back and fix that. Intramolecular forces, intermolecular forces. See, sometimes even your teachers can get it backwards. So intramolecular forces are within the molecule. So ionic bonds, covalent bonds are within the molecule. Now, with these 3 types, notice that covalent compounds have been broken down into 2, polar covalent and non-polar covalent. Now, polarity refers to an unwillingness to share electrons, essentially. So ionic compounds don't share at all. Polar covalent compounds are going to share electrons unevenly. Okay, it's like the bully or the your older sibling when they say that, oh yes, mom, I did share with my little brother and sister, but in reality, you know that they got to play with the toy for 20 minutes and you only got 2 minutes. They're sharing, but they're sharing unevenly. And then non-polar covalent would mean that it is electrons are going to be shared equally. And so we're going to use this chart to really help us determine if after we determine the electronegativity difference, which difference just means subtract in math, and this is the Greek symbol delta, which stands for difference, so it's just, again, telling you to subtract. We're going to calculate the difference between atoms to determine what type of bond it would form. Now, at the bottom of your page, you have a periodic table here, and these are electronegativity values. Okay, there's no way for you to solve this problem exactly without being given these values. So if you need them on a test or a quiz, they will be provided to you. And if we look at these practice problems, okay, if you look at hydrogen, and we want to see the most electronegative atom, well, between hydrogen and hydrogen, they're the same atom, and they're both right here, and it's got a electronegativity value of 2.1, so it's going to be hydrogen. The electronegativity, we would start with the highest, but since they're the same, it doesn't matter. It'd be 2.1 minus 2.1 equals 0. And we would take that 0, our difference, and we know that it's also equal to our triangle. And so we would come up here and we'd say 0 is less than 0.4, so my bond type must be non-polar covalent. And that's how we figure that out. So if we come back down to the next one, hydrogen and sulfur, we look and we see, okay, sulfur is 2.5, hydrogen is 2.1, so sulfur is going to be the most electronegative, and so we'll start with that. 2.5 minus 2.1 is going to give us 0.4. And if we look at our chart, 0.4, which I guess we need to amend this. If it's greater than or equal to 1.7, it's going to be ionic. And if it's greater than or equal to 0.4, but less than 1.7, we're going to have a polar covalent bond. And so we can continue to do all of these things, all these practice by doing the same thing and practicing using our chart. The cutoffs for the numbers are something that you're going to have to memorize. So that was the notes that we did in the first day of class. So hopefully you've caught up and you feel confident and ready to go.